the next one, which is parallel processing, which is another way to improve the performance of your code. In practice, actually, what's going to happen is that we're going to use both at the same time, both parallel processing and broadcasting. And I hope I will be able to show you this. But just one small disclaimer here. I'm not going to talk about parallel processing. Like parallel processing is very complicated, right? In general, then you have to do a course only on parallel processing. This is kind of like, what is the easiest possible way that I can do parallel processing in my code in order to make it faster, but without spending hours on this. So we're gonna treat some simple examples where it's very easy, very straightforward to do parallel processing, but the hardest parts are outside of the scope, okay, of this lecture. There's a bunch of text here that you can read later. So we start with this concept of an embarrassing parallel program or problem, let's say. Okay. What's an embarrassing? I think you will hear this concept or see it or read it in other places. What is an embarrassingly parallel problem? Why is it embarrassing? Something's called an embarrassingly parallel problem when it's so easy to parallelize it. There is basically like zero effort and zero trade-off. That is embarrassing if you don't parallelize it. Nowadays, everyone has at least 4 cores in their computers. So if you're not using these 4 cores, then it's kind of like, in a way, it's a little bit of a waste of resource. Because some problems are so incredibly easy to parallelize that if you don't, then you're basically losing, wasting resources. Now, this is a conceptual thing, okay? Of course, in practice, there are always a few things you need to take care of. But the thing is that conceptually, some problems are basically, they offer no restrictions to parallelization. So you can just parallelize them in very, very straightforward way. So that's why these are called embarrassingly parallel. This is an example of an Euclidean distance in pure Python, right? So this is basically the Euclidean distance between 2 vectors x and y. I start with as an empty. This is pure Python, okay, guys. We're gonna start with pure Python, and then we're gonna move on again to NumPy. But it's just as an example, I will start with pure Python. Basically, I'm taking 2 lists. I'm creating a new empty list. Then I'm looping over the vectors, calculating the squared difference between each element, and then take the square root of the sum here. This is basically Euclidean distance, okay? There's an alternative shorter implementation here, which I think is very interesting, and I will use it just so you guys can have a taste of what it is to write Python one-liners. It may look very complicated, but after a while you actually get used to this, and then you will never do this again anymore. I don't have the time today to explain what's happening here in details, but this is what is called a comprehension. Well, this one here is what is called a comprehension. A comprehension is basically just like an inline loop, right? It's a loop that does just one thing. And in this case, for example, it's a loop that is squaring the difference between 2 elements. And maybe the hardest part here to understand is this zip thing here. But the zip is a built-in from Python that lets me iterate over 2 arrays at the same time. So every time I call, so when I'm iterating over a zip here, basically I'm taking the first element from x and y, and then the second element from x and y, and the third element from x and y, and so on and so forth. So then I'm taking them, and then I'm squaring the difference and putting it into a list, okay? I don't expect you guys to understand what's happening here. I just wanted to drop this to kind of like raise your curiosity so that you can go outside and learn about comprehensions. Maybe I do a small video later only on comprehensions if there is enough interest, but right now I don't have time for that. But basically, this thing here does exactly the same as this thing here. So it's a good way also to compare and try to understand why this is the same as this. Okay, I'm just going to leave it there for now. So this is just Euclidean distance between two vectors, pure Python. Now, this would be an implementation of a distance matrix, again, Euclidean distance matrix, but in this case, everyone against everyone, right? So dumbest possible implementation, no vectorization, pure Python. I start with an empty square matrix. So again, dumb implementation here. If the X has n rows, then the D will have n by n. So it's like if it's 100, then it becomes 100 by 100, for example. And then I just, for every element, I just go out, take the Euclidean distance of those two elements, put it in the distance matrix, and so on and so forth. Quadratic, super slow, but that's how it is with pure Python. So the implementation here is inherently sequential and quadratic. So you have to actually go over all the rows and then go over all the columns and then compute everything, and quadratic. So it's really, really slow, right? I process each possible pair actually twice here because I process ij and then I process ji later, which could be one source of optimization here. And the result is a list of lists. So this is not an array. I'm working with pure Python here. The result is a list of lists, and you're gonna see why I'm doing this for now. So then, for example, if I do D1015, then that means I want the distance between rows 10 and row 15 of the original data set X, right? So then what I'm doing here is, oh yeah, I forgot to run this right here. So yeah, so then here I'm just loading the iris data set just as an example. The shape of iris is 150 by 4, which means that 150 rows and 4 columns or features. Then I calculate the distance matrix of iris, so Euclidean distance matrix. And then the shape of the iris is 150 and 150 because it's everyone against everyone. And then here I'm just using this pdist implementation here that is obviously the right way to go. If you want us to do this, you shouldn't do it yourself, but I'm just using it here in order to check whether my implementation is actually correct. And in this case, we're now using np.all_close in order to do the assertion. Like I said before, I'm not using all anymore. I'm using all_close. And basically all_close is the same as all, but it only checks up to a specific precision. And in this case, if I'm not mistaken, the default precision is 8 decimal points. So it compares the two distance matrices up to the 8th decimal. And then if they are the same, then that's okay. And then as an example, I just take again, like I said here, 10, 15, the distance between the 10th and the 15th element is 0.78, whatever. That doesn't mean anything. It's just a distance. Yeah, as it is right now, this pure Python implementation is very, very slow, right? So for example, I'm going to run this, and then you can see that for the iris data set is actually very fast because the iris data set is very, very small. So I'm running it here, and as you can see, I'm timing it as the Euclidean distance matrix. Then I give the X iris here. I'm just running it once because, you know, it already takes a while. But then I'm generating a random data set here. And again, pure Python, okay? You might be thinking, oh, why are you doing this? Why don't you do it in NumPy? But I'm just trying to make a point here of doing everything in Python, in pure Python for now. So I'm generating a random data set here with 1,000 rows and 100 columns. And then you can see that it takes 14 seconds. And I'm talking like about 1,000 rows, right? That's not much. I mean, nowadays, that's nothing, right? So that would be stupid to wait 14 seconds to do something like this. Obviously, you might be thinking, yeah, but you should use NumPy for that. Obviously, we should. But right now, I just want to try something a little bit different, which is to use parallel processing, because this problem is one example of an embarrassingly parallel problem. Because I have a matrix, and each cell of this matrix, or each row, or each column of this matrix, they could be computed independently because they don't depend on each other. There's no implicit sequence that I need to perform these operations. As long as I put them, of course, in the right place, right? So for example, if I'm computing the distance between the 10th and the 15th rows, then of course they must be in the right cell, which is D1015. But the sequence that I'm using to fill this matrix doesn't matter. Like I could put the second row first, and then then the first one, and then the last one, and then the middle. It doesn't matter. As long as I put them in the right place, the sequence that I'm putting them doesn't matter. So that's why it's an embarrassingly parallel problem, because there is no restriction. Like I could break this matrix down into small parts and then just throw them into different parallel processes or threads, let them do their thing, and then later when I get the results, it doesn't matter. It would work exactly the same. So basically it is like an obviously easy problem to parallelize. In order to make that point, what I did here was I just wrote a very simple new Euclidean distance matrix computation here, but I'm shuffling all the rows and all the columns before. This is exactly the same as the previous one, okay? It's exactly the same as this one. However, if you look at the for here, you can see that I'm actually iterating over the rows and then iterating over the columns in a random way. So basically, I'm just gonna fill up the rows and columns in anyway. Doesn't matter. Totally random. And then when I check the assertion here, whether this result of this thing is exactly the same as the result I got before, then I get a positive result here. Basically, the distance matrix that I got from computing everything in a completely random order was exactly the same as I did when I actually did them in order. So that means, yeah, this is embarrassingly parallel. Because the problem with parallel processing is that it's very unpredictable in many ways. So if you start 10 threads or 10 processes, and each of them is going to run a task, you don't know exactly the order in which these tasks are going to be executed, because there are many external factors that can influence that. And maybe the first thread finishes first, and then after that, the fifth thread finishes second, and then the third one, and then the 10th, and then the 8th. You cannot predict that. So as long as that lack of order does not matter to you, then it's embarrassingly parallel. Then there's no reason why you wouldn't do that, because then basically you're running things in parallel, and that's very good. Of course, there are many complexities here that I'm just glossing over, but basically that's what you should think. If I can do a bunch of operations in parallel, they don't depend on each other. Like I don't have to wait for one to finish before I start the next one, and the order in which they're finishing doesn't matter, then it's embarrassingly parallel. And you will see that happens many times. So even though it's the simplest possible type of parallel processing, it still happens a lot. So there's no reason why we would not do it, right? So how do you do it? Well, there are two different ways to do it. There are threads and there are processes. I'm going to talk mostly about threads here. And hopefully by the end of this notebook, you will understand why. Some people prefer to use processes. There are pros and cons. Okay, there are advantages and disadvantages for both. Personally, I use threads the most, and I'm going to explain to you why. And maybe if you ever try to use threads in Python, you might be scratching your head right now, but hold on, I will show you what I mean, okay? So without going into too many details about what happens with threads and what happens with processes, the workflow is basically the same, okay? You take your problem, whatever it is, you're looping over a bunch of stuff. In this case, for us here, we're looping over the rows of the data set and then computing the distance matrix. So anyway, you have a problem that is large. So you break your problem into small chunks, small parts. How small, we'll see. But anyway, you have to break it into some chunks. Then you start a new thread or a new process to execute each of these chunks. Again, whether it's a thread or a process, we're gonna get there. And then after all these threads or all these processes have executed have run like this chunks that you gave them, then you have to gather all of them back, and that will give you like whatever results you're supposed to get in the end anyway. So so basically, again, break a problem into chunks, run these chunks in parallel somewhere, and then gather all the results back, and then you have your results, hopefully. Very, very, very like general approach. Okay, again, lots of details are being glossed over, but 90% of the time, that's all you need. So how do you run a thread? Okay, suppose we wanted to run just one thread to just do one thing. This is how it works. This is the code over here. It's super simple. You import it from a certain library here, thread, then you have this class called thread. You instantiate this class by giving it a target and arguments. So David, this is a case where you don't have to wrap your function into something else, because you can give the function and you can give the arguments. So then you don't have to wrap it up in anything. You can actually call your function with any arguments that you need, right? So it's a bit, I guess, better in this sense. So target is a function, whatever function you want to run. In this case, I have this like a simple function. I give it some argument, then I start the thread. By the time when I start the thread, then basically, yeah, I'm giving it the okay, do it. And in this case, what this function is doing is just prints running in a thread. Then it does some time-consuming computation here. And I added a little bit of random values here just so that different threads will take slightly different time to run. And then just prints the results of this operation. Well, actually not the results of the operation, sorry. It prints the actual argument, and you will see why I'm doing this. And then after that, I have the end here, right? And you realize probably that you don't have, the end is actually not the end, right? So first you get running a thread, then you get the end, and then you get the actual results, or the actual second print here where I'm giving the argument back. So I hope this is not so hard to understand why this is happening, right? Because I've started a thread, like I said, okay, start this thread, but obviously the main program or the main thread keeps running also. So now you have two threads running in parallel. You have the new one that you created, and you have the actual normal program thread that's still running. So that's why you get the end, and then later you get x equals 1, 2, 3 after this thread here actually finished doing whatever it was doing. That takes a couple of seconds, I guess, or something like this. Now this is obviously problematic, like because our workflow is break it into chunks, run them in parallel, then gather the results. So how can I gather the results if every thread is running completely wild and I have no idea when they are actually going to finish, right? Well, obviously there is a solution, which is to join the threads. So when you call, so okay, obviously I have to save the thread first in this t variable here. But when I call join, basically I'm saying, look, stop here and wait until this thread is over, and then you can go on, because like this is the place where I'm gathering my results. This is a place where I say, okay, I need all the threads to be finished before I can go on with the rest of my code, because or else it's just too unexpected. I need to know the results before I move on. And you do that by joining the threads. Okay, I don't know why they use this name join and not wait or anything like that. I guess because two threads join into one or something like this. Probably that's why. So very important, join. If you don't use join, then you get all kinds of unexpected results that are not really useful. Now, of course, starting one thread is borderline useless. So what you really want is to start many threads, right? And this is the code to do that. Again, it's super simple. No secrets here. I have this list of threads here because I need to keep track of all the threads that are actually running because I need to join them later. So I create this list here. Then I just say, okay, for I in range 5, I want to start 5 threads. Then start a thread for here. The function is the same as I used over here, but I'm as an argument here, I'm sending the actual number of the thread. Okay, just so we know like the threads that are running or not. Then I start the thread. So basically like, okay, start this one, and then start the next, start the next, start the next. So we run the whole loop and then we start these 5 threads. All of them will run the same function, but of course they're 5 separate threads. So this function is being run 5 times in parallel, more or less in parallel. And then I append this T thread to the threads list. And then after the loop is over, then I immediately ask the threads to join. And just remember, joining does not mean like interrupt or anything. It means literally just wait for these threads to be over before I go on. And in this case, it's a little bit different than here because here I'm joining just one thread, and here I'm joining all the threads. So I'm asking for all the threads to be joined before I move over to the end. And I mean, you still get a lot of bizarre, weird results here, but the end is actually the end. So that is guaranteed to happen. Like the end will always be at the end because I'm saying I only allow this to go on after every thread is joined. Okay. But of course, in the middle here, you get a lot of bizarre stuff. And the reason why you get a lot of this weird results is because every thread is running this function, and this function has a little random, execution here. And I want this to do this exactly because I want this to show you that this is a very good, like this is a simulation of what would happen in reality. In reality, there's a lot of stuff that could change. You simply don't know. Okay, you cannot expect to know what's going to happen after you start the threads. They're just going to do their thing in parallel, and then afterwards you're going to gather them. But in between, while they're running, unless you use locks or some more advanced stuff that we're not going to get into, you can do it, but we're not going to talk about that. In general, you just say, okay, there are 5 threads running. I don't know exactly what's going to happen. I don't know exactly which ones are going to finish first or second. I just know that they're running, and then afterwards, I just want to gather them all and then do something. So then you can see that x equals 1, which is the second thread finished first, and then the first one, then the third one, the fourth, and the fifth. So you can see that is, I mean, if you run this many times, every time you're going to see something different because it's random. So all these weird like running in a thread things here, and you can see here, this is even weirder because one of the threads started to print, and then the other one got in the middle and printed, and then the previous one finished. So this is completely bizarre because everything is just completely working in parallel. So you can't really expect anything to happen here. And print is not thread safe as we say. So it doesn't care, like it just tries to print, and then something else comes in and tries to print on top of that, and doesn't completely, there's no guarantees here. And so you shouldn't, the bottom line here is don't try to control what's happening here. Just say, okay, I have 5 things running in parallel. I don't know what's going to happen. Let them run. And then afterwards, I'm just going to gather all of them. And then I can actually expect to have something after I join them. Okay. I hope that's clear. I'm not getting any questions. So I hope the message is actually coming through. So now we're ready to implement our multi-threaded version of the Euclidean distance matrix. And this is where it is. So basically, I broke down a small sub-function here called task, which is what each thread is actually going to execute, right? And basically, it's just the Euclidean distance between 2 vectors. But I'm also putting the responsibility in the thread to actually take this value and put it into the matrix. And the reason why I'm doing this is because this thread thing, it does not return anything. So previously, I could simply take the result of Euclidean distance and assign it to the matrix inside of the Euclidean distance matrix function. But I can't do that here because when I start a thread, I don't get a result. I don't get a returning value. So instead of that, I give the matrix to the thread and I say, look, fill it up yourself. It's exactly the same. It's just an inversion here in the direction of the thing. So very simple, Euclidean distance matrix threaded. So I start with an empty square matrix, then I'm looping over all rows and all columns exactly as before. But then instead of doing this here, which is the previous implementation, instead of actually computing the Euclidean distance and assigning it to the matrix, I'm starting a new thread to run my task, and I give it the arguments. I give it the D, which is the distance matrix that's supposed to be filled. I give it the data, I give it the row, and I give it the column. I give everything. And then the task actually runs. So this runs in a thread, okay? In each thread. Then I start the thread. I append the thread again to my list. Then after all of this is done, I join all of them to make sure that everything is done. And then I return the distance matrix. And then we run the benchmark and yeah. And then we run the benchmark, right? 300 rows by 100 columns, just one random data set, whatever. And then I'm running the Euclidean distance matrix, which is the original one. And I'm running the threaded version of the Euclidean distance matrix. And then again, asserting if they're the same, and then I time it, okay? And if you look at it here, you might be surprised to see that actually the second one was lower. And I should have written something here to make it easier. So the original is the first one, and the threaded is the second one. So you might be very confused and very surprised to see that the threaded version is actually much slower than the original one. We were trying to get a performance by parallelizing stuff, and what we did was we just completely screwed up and made it much, much worse than before. So that is a problem. Not only we did not get any improvement, but we actually made it slower. Now, why is it the case here? We are starting a new thread. I will answer David a little bit later. So we are starting a new thread here for every single cell of the distance matrix. And starting a new thread is not for free. There is an overhead involved in actually starting a new thread, right? So that's why we get a lot of a big hit here in the performance, because we're actually starting, like for the iris data set, which is, well, we're not using the iris data set here, so I changed it. So but with the iris data set that has 150 rows, we're actually starting 22,500 threads. That is a lot. And for this one, we're actually doing it even worse. We're actually starting, how many, like 90,000? Is it 90,000 threads? I think, yeah, 90,000 threads. So that's a lot of threads. Like there's simply too many threads. And the lesson to be learned here is that you need to try to find a balance between how many threads you start and the workload of the thread. Because right now we're starting 90,000 threads, and each thread is doing something very, very simple. And it's so fast that basically it's not even worth it for the thread to start itself just to do something that's so fast. So you're basically starting like 1 million threads to do something that's so small that the overhead of starting the threads is larger than the actual performance that you should be gaining from this. So I rewrote it over here. And now what happens is, instead of starting a new thread for every cell of the matrix, I'm starting a new thread for every row of the matrix. So for every row, I start a thread with these like task number 2. And the test number 2 now that runs inside the thread is actually running in loop and is computing the entire row of the distance matrix within the thread. So every thread now has more responsibilities, so it's doing more, and there are less threads that are running, right? So that's usually what you want. You want to find the balance between these two things. You want to find the balance between how many threads you start and the actual workload of a single thread. So in this new version, we start only, so to speak, n threads. So in this case, it's 300. So that's kind of like, that's okay. And then well, good. We don't have this huge performance hit anymore, but we also don't have a good results here. We basically stayed the same. Actually, we have exactly the same performance as the non-threaded version, with a little bit of an overhead here for actually starting the 300 threads. And there's a reason why this is happening. And that's because of the global interpreter lock, which I'm going to discuss now. David has a question. Is there a maximum number of parallel operation? Not a maximum. Not like a static fixed maximum. But what happens is, again, that if you just start too many parallel operations, then the overhead of starting each one overcomes the performance that you're supposed to get. So it's up to you to find a balance, and I will get to that, and I will give you a little bit of a good advice for this. But a fixed number, maybe, not that I know of. Maybe you can, I don't know, maybe if you start 300 million threads, something could happen, but I'm not sure. Yeah, it has to do with your hardware. Yeah, exactly. I will talk about this. It has to do with how many cores you have. Now, the problem here is that we did not get a performance improvement as we wanted. And there's a reason for this. And the reason is because of this thing in Python that's called the global interpreter lock, or the GIL. And basically, I'm not going to get into details of the GIL because it's mind-blowing. But basically, that's what happens with the GIL is the GIL does not let more than one thread to be executed at the same time in the Python interpreter. Okay. So before you think about killing me, like, why did we do all this if you cannot run actually threads in parallel? Hold on, because we're going to get there. I'm going to show you that that's not exactly the case all the time. There's a caveat, and a very important caveat. But in general, if you're running pure Python code, and that's why all I did so far was in pure Python. If you're running pure Python code, you cannot run more than one thread at the same time in the Python interpreter. So you cannot get more performance than you would get from just not using threads. Because even though you have the threads are all running one at a time. So one thread stops, the next one starts. And then a little bit of that thread runs, then it stops, and the next one starts, and so on and so forth. So there is no parallel execution if you're using pure Python code. Okay? But I'm going to get to that, and I'm going to explain to you why. I did a quick detour on processes here, but I'm actually going to skip this in order to focus on the threads. But just know very quickly that that is not the case for processes. Okay? When you start a new process using the same way that you started a new thread, that actually runs in parallel, even if it's pure Python. Okay, but the problem is that there are two problems with processes, which is the overhead of starting a new process, which is much larger than the overhead of starting a new thread, and communicating between processes is also a very complicated process. So that's why I'm going to skip processes, and I'm going to show you how to actually use threads in a nice way. You can go back here and look at the process examples later. Or maybe if you want, I can even extend myself a little bit and talk about processes. But for now, I will stick to threads because it's more important. Okay. So does that mean that threads are useless in Python? No. Why? Because when you're running code that is not Python, so for example, NumPy, which is native code, that runs outside of the GIL. That runs outside of the global interpreter lock. So whenever you start a NumPy operation, since that goes outside of the Python interpreter and it runs on actual native code, then that releases the lock. So if you start 4 threads and each of the threads is running a NumPy operation, then they will actually run in parallel because they're outside of the Python interpreter. And everything that's outside of the Python interpreter is not held back by the GIL. Okay, so let's see some examples here. I updated the task here to be actually using, now we're using NumPy, right? So numpy.square root, numpy.sum. This is a NumPy vectorized operation. It's a broadcasting actually. I'm broadcasting a single row against the entire matrix. And then I square it, and then everything, I sum it, blah, blah. So this is this is Euclidean distance in a line, in one line in NumPy. And then I assign it to the row I. So like I'm computing each row here in a thread, right? Which is like what we did before. First I was computing each cell, then that was too much, and then I was computing each row, and then that sounded like a good balance. So that's what I'm doing here again, but now it's only with rows. Sorry, only with NumPy. So it's basically a pure NumPy operation here that is running inside each of the threads. Okay. So that's why I need to cast the X into a NumPy array so that I can use NumPy operations. D is also a NumPy array now. It's not anymore just a list of lists. It's an actual NumPy array. But the rest is the same. I'm looping over the rows. For each row, I'm starting a new task, which is this task number 3. I'm giving it the arguments. Then it does what it has to do, like it computes a row. Just the same. Start the thread, append the thread, join them, so on and so forth. It's exactly the same as before. And now when you look at the performance, we got a very good improvement in the performance, right? So now the original one was 1.36. I mean, we can even, I guess, make it a little bit larger, and you will see that the pure Python one grows much slower. Yeah. So you see that the gain here was really good, right? And again, let's review this. Why is it that it worked now? Because this is not being held back by the GIL anymore. Since each task is running a NumPy operation, every time this operation here starts in a thread, it runs in parallel. Because basically you step outside of the Python interpreter, and now it's NumPy's responsibility to calculate this, and NumPy is not, it's not held back by the GIL. So lesson to learn here. If you're using threads, everything that you do in a thread, or at least you should try to do mostly NumPy operations in a thread. If you do that, you're fine. If you do too many Python operations within a thread, that will slow you down because the Python operations will not be parallelized, okay? That's the lesson to learn. Now, this is good. This is really nice, but we can do much better. Actually, this is not that much better than what you would have if you actually would run this thing without threads, but purely in NumPy. So if you re-implement this and you remove threads altogether and you use just NumPy without parallel processing, you would get something close to this. So what we can do here is to go even further into that thing that we discussed before, which was that the threads are still too lightweight. And the reason why they're lightweight here is because this thing here is so fast for NumPy. This is computed really, really fast for NumPy because it's completely broadcasted, vectorized, native code, everything. So this operation here is so fast that, again, we're back at square one where we said each thread is like more expensive to start a thread than to actually execute it. So again, we need to think about how we can give more responsibilities to the thread to make them run longer and reduce the number of threads so we don't have the overhead of starting millions and millions of threads, right? So in this case, we're starting actually 500 threads, and each one is doing this. And this is so fast for NumPy that doesn't really, I mean, it's better than the previous one, but we can do better than this, okay? So my final version of this implementation is a chunked version. And this is usually, this is very close to what you would get if you actually used an external library. Actually, this is faster than the external library that I tried. This implementation here, I re-implemented it using joblib, which is an external library that does parallel processing, among other things. And this was faster in my experiments. Who knows? So, of course, it's custom made for my specific problem. Anyway, it's a chunked implementation. So what does that mean, to be a chunked implementation? While in this case here, I was basically starting a new thread for every row. So if the rows of the data get bigger, then my threads, then I have more and more threads, and I can't control that. And that's a problem because I don't want that. I want to have actually less threads, not more. So, so what I do is I take this in chunks. You can see here that I have this thing called the number of jobs, and this is related to what David was asking. For example, I have 8 cores in my computer. So I'm determining that I want to run 8 jobs. So I want actually 8 threads. I don't want any more than 8 threads. I'm fixing the number of threads into 8. And then if my number of threads is fixed, then I need to somehow distribute the workload in these 8 threads in such a way that they can run in parallel and get a lot of, as many performance gains as I can. So how do I do this? Well, I calculate the chunk size, which is the size of the data set. Well, the number of rows divided by the number of jobs. So like if I have 8,000 rows and I have 8 jobs, then I have 1,000 rows per job or 1,000 rows per thread. So a thread is not going to run just a single row anymore. It's going to run a bunch of rows. And this number is determined by the number of jobs that I want to have. So if I want to have 8 threads, then each thread is going to run 1/8 of the complete size of the problem, right? And this is a very good balance between the workload of a thread, so each thread gets a lot of work to do, and not many threads are started at the same time. So usually that's good. It's a good balance. And this is related to what David asked me. Is that related to how many cores you have? Yes, because I have 8 cores, so I'm starting 8 jobs. Some people will tell you, start a couple of jobs extra. Not exactly the same number of cores you have, because some cores will finish before the others, and then you want to keep them busy. That's a good advice. Some people say run double the amount of cores you have. I guess that also works. I could run 16 jobs. I mean, it wouldn't make that much of a difference, but still it's good because some cores will finish first and then you can keep them busy. So they're not idle. They're not just there not doing anything. And what I had here, yeah, okay. What I have here is then I define the chunk size. I get like the number of jobs and divided by, well, the number of rows divided by the number of jobs. This is related to the questions I'm getting. I'm going to get there. And then just so I explain to you the task here. And then I'm starting. You can see here that the loop has changed a little bit. So I'm not looping over the rows anymore. I'm looping over the chunks. So I start at 0 and then I go chunk by chunk. So that's like the first one is 0. The second number here, it was going to be, I don't know, 1,000, then 2,000, 3,000, so on, depending on the chunk size here. If the chunk size is 1,000, then I'm getting 0, and then 1,000, then 2,000, and 3,000. I hope this is this syntax here is more or less familiar to you, because this is the step size that I'm taking here. And then I'm sending it to my tasks. And the task here is using this thing called a cdist. Now this is, we could do this manually, but I thought it was interesting to show this to you, how it works. This comes from scipy.spatial.distance. And basically this is like a pairwise distance computation, but it doesn't require the two sides of the pairwise, let's say, to be the same. So for example, in this case, I'm computing all the distances between a chunk of the data against the entire data. So it's a little bit like what I did before, where I was computing one row against the entire data. But in this case, I'm computing a chunk of rows against the entire data set. And I'm doing this with cdist. We could implement this ourselves using broadcasting or anything like that, and it would still work. But I guess it would. I thought it would be nice to introduce you to this, because this is super useful, and you're probably going to use this a lot. And there is a small problem here where I'm actually, this is the correct one, not that one. I'm not sure why I did this. So yeah, so then I'm starting the chunks, and then I'm going to check, yeah, and then I got, this time I'm testing it with a bit more than before, but if you want to compare it with the previous one, then we can use the same. Yeah, so I'm comparing here the performance between the third version and the fourth version, was the final one, and I get like almost 8 times faster than it was before, just because I reduced the amount of threads and I increased the amount of the size of the chunks that I'm computing at the same time. Then I get a lot of improvement. And this is a very good implementation. Okay, we can go like this, 5,000, and you can just keep going. And the third implementation here is going to get quite slow. But the other one is actually going to stay fast, so you can just keep going, and it's no problem actually. Now, some questions. What if we have 9,000 rows and 8 cores? This is from Satirios, and David asked, what if chunk size is a float? I guess both of the questions are the same. What happens when you don't actually can divide everything nicely into specific chunks? In that case, you should probably deal with that, and then you would have, let's say, one final chunk where that's a little bit different than the others, and then you have to kind of deal with that. I'm not dealing with that here. I oversimplified the problem here, but you're absolutely right that we would need to somehow deal with that here in order to make sure that we're actually treating all the rows of the matrix here. I'm not sure exactly if this would be a problem in this specific implementation, but there might be a problem. So you don't need to have all chunks to be exactly the same, right? I mean, hopefully you distribute the operations in the nicest possible way, so that you can actually have many threads running at the same time doing the most work. But obviously sometimes you will not be able to, so it's okay to have a couple of chunks that are a little bit different than the rest. That wouldn't be a huge problem, but you have to deal with that somehow. The important part is that I guess I exaggerated here, and this is probably going to take a couple of minutes, so I'm going to interrupt it. Yeah, so that's it. That was basically where I wanted to get. Let me go with 10,000 instead. This is where I wanted to get with threads. The most important part here is these lessons that you need to learn. Like, first of all, don't start so first of all, pure Python does not work to parallelize threads. So if you have code in pure Python, then threads are useless mostly. So threads only work if you actually have NumPy code, mostly NumPy code. So if you want to use threads, stick to NumPy. Second thing is, don't start too many threads, too many lightweight threads. So look for a balance between the amount of workload that you put in threads and the number of threads that you're actually starting. And then there's processes. Now I will finish this, at least this part here. My computer is a bit slow right now. I guess I should have. Oh man. So so threads. There were advantages and disadvantages to threads, and advantages and disadvantages to processes, which is written here somehow, but my computer is already. Yeah, there you go. So it's, as a summary, there are advantages and disadvantages to processes. The workflow is more or less the same. So actually everything we did with threads and processes, basically the API is exactly the same. But the advantages of using a process is that you can parallelize any Python code. So if you start a new process to run a certain task, that will run in parallel, because that's a new process, is in a new completely program running completely separately than your previous one. Okay, so that parallelizes anything. What are the disadvantages of processes? Well, first of all, they are very slow to start. So much slower than actually threads. Oh man. So they're much slower than threads to start. So then this thing about balancing the workload and the number of processes to start, it makes much more difference than with threads. But the most important disadvantage here is that it's very hard to communicate with processes. You cannot do the same thing that we did before with a process, like for example, this thing here. You cannot send a distance matrix to a process, ask the process to fill that distance matrix, because then after the process does this, you cannot get it back. Because what happens here is that one parent process starts many child processes. And the parent, it's very easy for the parents to send the data down to the child, to the children process. So the children will get the distance matrix and they will fill it like this. But afterwards, when we want to gather all these data back and then have a unified distance matrix, then that takes a lot of work, because then you have to actually use specific data objects that will allow you to do that. And that gets a little bit complicated. So that's why I didn't want to focus on this, because since I think all of you guys are actually going to use NumPy code most of the time, then threads are perfectly fine. As long as you're using a lot of NumPy code, threads are perfectly fine. And a thread has this nice advantage that you don't have to worry about communicating. So everything that's available here is available here, and they just go back and forth and no problem. Of course, if one thread starts writing into the same area as the other thread, then you will get unexpected results. But as long as you have these embarrassingly parallel problems where every thread is just working with its own memory, well, at least its own positions in the matrix, and one is not like getting into the other one space, then it's absolutely fine. So the advantages of threads are lightweight, very cheap to start. They're not free, but much cheaper than actual processes. They're easy to communicate with because they basically share this, and you don't have to worry about anything. The variables are just basically just available. And the disadvantages of threads is that it only parallelizes code that releases the GIL. So again, if you're running Python, then you cannot parallelize it because, you know, it has a global lock.